Hi, everyone. This is one of our last two science videos. Before Mr. Gilson changed the date that we would be finished from May 29th to May 21st, I thought I'd have a lot more time to teach you about Chapter 10, which is about light. But since I only have 2 days, I'm going to kind of do like a crash course where I cover some of the material and talk to you about it, just so you're introduced to it. And here's what you're going to do during the video. While you're watching this, I want you to write down 5 things that are new to you, or that you think are really interesting, or that are something you've never heard of before, but you really think is cool. Anything like that. But I would like you to do 5 different things from this video that you learn. And that way, then you'll put it in LMS. You'll just type the 5 statements into LMS, 5 things you learned. That will show me that you watched the video and that you were paying attention and that you figured out some things from the video. So the unit that we are talking about is light. So I would like you to turn in your science textbook, if you're not already there, to page 237, the intro page, which is going to introduce us to a very interesting woman from history who did some amazing things. During World War I, there was an army dedicated to saving lives instead of taking them. This army of doctors and nurses cared for soldiers who had been wounded in battle. But how could they look inside a soldier to see what was wrong? Marie Curie, a Polish chemist and physicist, knew that the X-ray, a recent development in technology, would be helpful in solving this problem. She studied human anatomy and how to use the X-ray machines. She even researched how to work on cars. Then she gathered 20 vans with the equipment for taking X-rays. She and her daughter drove to the front lines to help the doctors care for wounded soldiers. Her X-ray trucks were called Little Curies. By the end of the war, she had set up 200 X-ray stations in military hospitals. She also directed the training of many people in the use of X-rays. Because of Marie Curie's work, many soldiers healed faster and many lives were saved. So on the PowerPoint, you see a picture of, there's Marie Curie. She was a Polish chemist and physicist. She figured out how to use X-rays to see inside the human body. Before that, soldiers who were wounded, if you remember from our study of the Civil War, pretty much the only thing they could do was amputate and cut off the wounded limb. If you were shot in the leg, they cut off your leg. If shot in the arm, they cut off your arm to save your life. Well, now that X-rays have been discovered, she figures out how you can use X-rays to see inside the body and see what is wrong. This helps doctors to diagnose. They can see where the bullet is. They can take bullets out more safely. And many, many soldiers' lives are saved, and many of them heal much more quickly thanks to this new technology. This is a picture of a Little Curie. Remember, she and her daughter set up 20 trucks with X-ray machines in them and drove them to the front line. So they went right into the battle. So Marie Curie is an American hero. She's a hero, not just for America. She's a world hero because she helped save the lives of soldiers. So she used X-rays, which is part of light. And the unit that we're going to do a quick dive into is the unit about light. So now I would like you to look at the next page in your book, page 238, light energy. The people who first discovered X-rays many years before World War I were surprised and amazed by what these mysterious rays could do. It was as if they were a kind of invisible light that could shine right through solid objects. X-rays share many of the same characteristics with the light that you can see. Characteristics of light. Light is a form of wave energy. It is constantly moving throughout the universe. A light ray travels in a straight line, but the matter around it moves up and down. Light waves spread out as they move away from their source, like ripples of water move away from the place a pebble is dropped. However, Light travels much faster than water. If you could travel at the speed of light, you will be able to go around the world about 7.5 times in just 1 second. Though light waves carry energy just as other waves do, light waves are different from many other kinds of waves. The energy of water waves and sound waves must move through matter. Remember, we talked about that. Sound waves are mechanical waves. They must have matter to travel through. Light waves, though, can move through both matter and empty space. Because light waves can travel through space, light from the sun and other stars can reach the Earth. So the difference between a light wave and other waves is that it can travel through empty space. It doesn't have to have matter to travel through. And we can see that because the light from the sun travels through empty space so that it can hit the Earth. Light waves also move faster than other types of waves, such as sound. Light can travel through space at about 300,000 kilometers per second, 186,000 miles per second. The sun is about 150 million kilometers, 93 million miles away from the Earth, yet light from the sun reaches the Earth in about 8 minutes. Scientists do not know of anything that can travel faster than light does. So my first slide up here is that light is a form of wave energy. It can move through both matter and empty space, and it travels 300,000 kilometers or 186,000 miles per second. And it takes light from the sun about 8 minutes to get from the sun to the Earth, traveling 93 million miles. So that's the first really interesting thing about light, how fast it travels, and that it doesn't have to travel through anything. It can travel through empty space. So the next few slides talk about the same thing. Light is considered an electromagnetic wave because it can move through empty space. So when you see that electromagnetic wave, that is a wave that doesn't need anything to travel through. We talked about mechanical waves like the sound wave. Those have to have matter to travel through. Longitudinal waves are waves that move in the same direction as the matter is moving. When we saw the example of the slinky, the wave is moving in the same direction as the matter. And an example of a longitudinal wave is a sound wave. There's an example. There you see the compression and the rarefaction. So these are longitudinal waves. It travels in the same direction. But light, light is called a transverse wave because the wave moves perpendicular to the way that the matter is moving. So that is the difference between a transverse wave and a longitudinal wave. When we look at transverse waves have crest, the highest point of the wave, and they have troughs, the lowest point of the wave. So crest is the highest, trough is the lowest point of the wave. The height of a wave is its amplitude. Okay, so if you ever hear about the amplitude of a wave, that's just the height of the wave. And a wavelength is the distance between two crests or the distance between two troughs. That would be a wavelength. And we talked about this in our sound unit. Frequency is the number of waves that pass a certain point in 1 second. You can see low frequency wave, medium frequency wave, and high frequency waves. And this is showing you a wave that has a frequency of 7 waves per second. This is the one that has 9 waves per second. All right, I'm going to show you a short part of a video. And just to talk a little bit more about waves. Oh, here we go.
Here we have an ordinary piece of rope. It's not one of those magician's ropes that can mysteriously be put back together once it's been cut in half. And it's not particularly strong or durable, but you might say that it does have special powers because it's going to demonstrate for us the physics of traveling waves. Ropes and strings are really good for this kind of thing because when you move them back and forth, The movement of your hand travels through the rope as a wave. By observing what happens to this rope when we try different things with it, we'll be able to see how waves behave, including how those waves sometimes disappear completely. How's that for a magic trick? This is a typical wave, and waves form whenever there's a disturbance of some kind. Often when something about the physical world changes, the information about that disturbance gradually moves outwards, away from the source in every direction. And as the information travels, it makes a wave shape. Think about the disturbance you cause, for example, when you jump on a trampoline. When you hit the trampoline, the downward push that you create moves the material next to it down a little bit too. And the same goes for the material next to that, and so on. And while that information is traveling outward, the spot where your feet first hit the trampoline is already recovering, moving upward again because of the tension force in the trampoline. And that moves the area next to it upward too. This up and down motion gradually ripples outward, covering more and more of the trampoline. And the ripples take the shape of a wave. Waves are made up of peaks with crests, the bumps on the top, and troughs, the bumps on the bottom. They have an amplitude, which is the distance from the peaks to the middle of the wave. They also have a wavelength, which is the distance between crests, a full cycle of the wave, and a frequency, which is how many of those cycles pass through a given point every second. Multiply the wavelength by the frequency and you get the wave speed, how fast it's going. And the wave speed only depends on the medium it's traveling through. That's why the speed of sound, which is a wave, doesn't depend on the sound itself. It doesn't matter how loud or quiet it is, it just depends on whether the sound is traveling through, say, air or water. Now there are four.
Okay, so that is the part of this video that we're going to watch, because you saw where that said physics crash course. So if you're interested in this kind of science, we learned about sound waves and now we're learning about light waves. This is called physical science. And it's kind of like the very beginning of learning about physics. So if this is something that interests you, then you are going to want to take a course called physics once you get into, I believe it was available to my sons and daughter in high school. So this is the kind of like the very, very beginning of a physics class. So if we look at page 239, it says comparing waves. Sometimes scientists classify waves by whether or not they can move through empty space. Waves that can move through space are called electromagnetic waves. Light is an electromagnetic wave. Waves that can move only through matter, such as sound waves, are called mechanical waves. So that's one way we can classify a wave. It's either electromagnetic, it can travel through empty space, or it's mechanical, it must have matter to travel through. There's another way to classify waves. Scientists also classify waves by the direction in which they move. Sound waves move in the same direction as the matter is vibrating. Waves that travel this way are called longitudinal waves. Light waves move differently. If you make a wave with a rope, you can see the wave traveling from one end of the rope to the other. As the wave travels forward, the rope moves up and down. The direction that the wave travels is perpendicular to the up and down movement of the rope. This is an example of a transverse wave. Waves that move perpendicular to the way that the matter is moving are called transverse waves. Light waves are an example of transverse waves. So another way to classify waves is how they move. Longitudinal waves move in the same direction as the particles, and then transverse waves move perpendicular. All right, now we're turning to page 240. On page 240, it says properties of waves. There are many different kinds of waves. Some are tall, others are short. Some move quickly, but others move slowly. All waves, though, have the same basic properties or characteristics. These properties include wavelength, amplitude, frequency, and speed. So no matter what size the wave, no matter how tall or how short, they're all going to have these characteristics. Transverse waves look like a series of hills and valleys, as you can see here. And let me go back to the slide that will help us with that. There you go. Okay, transverse waves look like a series of hills and valleys. The top part of a hill in the wave is called the crest. This is the highest point of the wave. The trough is the lowest point or valley of the wave. Scientists use the crest and troughs of a transverse wave to measure the length of that wave. Its wavelength is the distance between two crests or between two troughs. Another property is the amplitude of the wave, which we see demonstrated on this slide. Amplitude is the height of a wave. If you stretch a rope tightly, it will be in a straight line. Think of this straight line as the rest position of a wave. Moving one end of the rope will make the rope vibrate up and down. Part of the rope will move above the rest position and make the crest of the waves. The rope will also move below the rest position, forming the troughs of the waves. The distance that the rope moves above or below the rest position is the amplitude or height of the wave, which you can see here, amplitude. All right, page 241 says, as the rope moves up and down, many waves move through it. This shows the wavelength, and I'm going to get to frequency again. Each wave has a crest and a trough. You can count the waves passing a point by counting either their crest or their troughs. The number of waves that pass a certain point in 1 second is the frequency of a wave, which we also talked about in our sound unit, so that should be a familiar concept. A wave's frequency is not the same as its speed. Remember, we talked about that in our sound unit as well. Frequency refers to how many waves pass by a point in 1 second. Speed refers to the distance that one wave travels in 1 second. All waves have specific speeds, frequencies, amplitudes, and wavelengths. In the little box on the page, it says science and math. It shows you the formula for how to calculate the speed of a wave. The speed, wavelength, and frequency of a wave are related mathematically. If you know the wavelength and the frequency of a wave, you can calculate its speed. Suppose a wave had a wavelength of 6 centimeters and a frequency of 5 waves per second. The speed of the wave would be 30 centimeters per second. So the formula is wavelength times frequency equals speed. So there you go. Wavelength times frequency equals speed. This will be something that you will work more with in middle school, and honestly in high school. My daughter took physical science, and she did more of the mathematical side of physical science when she got into high school. So this is, like I said, a really little introduction, the first little step into physical science and physics. So now that we've talked about some characteristics of a wave, we're going to talk about light. So you're going to turn the page, and you're going to see on page 242 the visible spectrum. Probably heard about this before. Looks like a rainbow, okay? If you try to walk through a dark room, you may stumble or bump into things. Without light, there is no vision. You see objects around you because light bounces off of them. Light makes things visible or able to be seen. Light also gives objects color. In 1672, Isaac Newton proved that light is made up of many different colors. Newton used a prism to separate white sunlight into a band of many colors. The different colors of light that we can see are called the visible spectrum. And you can see it's the colors that you memorize for the rainbow: Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. That is the visible spectrum. Refraction and reflection. Light generally travels in a straight line. The direction and speed may change, but its path will usually be straight. The matter through which a wave travels is called a medium. So when light travels through something, the thing it's traveling through is called a medium. The speed of light changes as light enters different mediums. Light travels the fastest in empty space. It slows down a little when it enters air. Things such as a glass or water makes light slow down even more. When it enters a new medium, light slows and can bend in different directions. Refraction, that's my next slide. Refraction is the bending of light as it passes from one medium into another. And you've probably seen this before when you put the straw in to the cup. It looks like the straw is broken, but it's because of the bending of the light that you can see in this example. Prisms separate light into colors by the process of refraction. As sunlight passes through the air and enters a glass prism, the light slows down and bends. Each color of light has a different wavelength, so each color bends a little differently. This allows you to see the separate colors. Refraction also happens in a rainbow. Sunlight passes through raindrops and bends into the separate colors of the visible spectrum. The colors in the visible spectrum are in order by their wavelengths. The reds have the longest wavelengths. The colors after the reds are oranges, yellows, greens, blues, indigos, and violets. The violets have the shortest wavelength of the colors. You can remember the order of the color group by thinking of the first letter of each, which you probably learned like way back in kindergarten or first grade. The first letter spell out the name Roy G. Biv. And you can see that picture of the light being bent by the prism. Refraction, we're at the top of page 243. Refraction is one way that light changes its direction. When light hits transparent matter, remember, transparent, something that light can pass straight through, it passes through with little bending. Objects behind transparent matter are clearly seen. When light hits translucent matter, like this cup would be an example of translucent, some light passes through and some is bent or blocked. Objects seen through translucent matter appear unclear. Light slows down and bends when it passes through transparent or translucent things. Opaque matter does not let any light pass through. All of the light either bounces off the object or is absorbed or soaked in. All right, so now I'm going to show you our next video, which talks about the visible spectrum. So here we go.
When a beam of light hits a piece of glass straight on, it passes right through it. But the waves that make up the light actually get slowed down by the glass and only go back to their normal speed when they come out the other side. That slowing down is what causes white light to split into a rainbow of colour whenever it hits glass on an angle. It happens because glass slows some colours of light more than others, and because slowing down on an angle makes light bend. It's easy to understand the bending if you picture how the light waves would look from above, like how waves at the beach look if you see them from the air. And while white light's made up of all the different colours of light, it also helps to look at them one colour at a time. When a wave front of red light hits glass on an angle, the part of the wave that enters the glass first gets slowed down before the rest, and that changes the angle of the whole wave, like how waves bend around a cliff. Violet light gets slowed down even more by glass, so its waves bend more. All the other colours get bent somewhere in between. So the colours get separated when they first enter the glass on an angle, and they spread out even more when they speed up on an angle as they leave. The reason the different colours slow down different amounts in glass is because they've got different wavelengths. Red light has the longest wavelength, followed by orange, yellow, green, blue, indigo, and finally violet with the shortest wavelength. And the shorter the wavelength, the longer it takes to travel through glass. That's because light interacts with electrons in the molecules that make up glass. Long wavelength light, like red, only interacts a bit with the electrons, so it doesn't get slowed much. But shorter wavelength violet light interacts more, so it gets slowed down more. So it's the combination of hitting glass on an angle and different wavelengths interacting with the electrons in the glass different amounts that makes light hitting a prism spread out into a beautiful spectrum of colour and some classic album cover art.
Okay. That video hopefully gave you a little bit more of an explanation of how a prism breaks light into the visible spectrum. Now we are still on page 243. Second column. Light can change direction by reflection. Reflection happens when light bounces off of an object, and here's an example of that on the screen as well. The color that you see is determined by which colors are reflected and which are absorbed. You see the reflected wavelengths as the color of the object. A red book reflects the color red. All the other colors of light are absorbed. When all the colors of light are reflected, you see white. You see black when all the colors of light are absorbed. Why are darker colored clothes usually warmer? Darker colors absorb more of the light energy from the sun. The sun's energy makes the molecules in the clothing move faster. The temperature of the clothing rises and keeps the person warmer. Look down at the bottom where it says science and the Bible. God often uses light as a metaphor. In Psalm 119:105, the writer describes the Bible as a light unto my path. Just like a light shows you where to walk at night, God's words show you which choices are right and safe. Sadly, many people do not like this light because they live in spiritual darkness. In John 8, verse 12, Jesus said, I am the light of the world. He that followeth me shall not walk in darkness, but shall have the light of life. Through Jesus, people can move from the world of darkness to the world of light. Just a little reminder that the Bible is our light. It lights our path and shows us the good choices and the safe choices that God wants us to make. God's rules are for our protection and for our benefit. All right, now we're going to talk about color. So look at page 244. First, the basic, the primary colors. I know Mrs. Omisami teaches you about this. The primary colors, red, yellow, and blue. Look at page 244. Combining colors. An amazing variety of color is all around you. Whether a beautiful blue sky or a bright yellow flower, the world is full of colors reflected from our sun and white lights. Scientists study color using the idea of a color model. There are different color models, but each has 3 primary colors. Primary colors cannot be made from other colors. God designed our eyes and brains to combine primary colors into all of the colors that we can see. The primary colors of light are red, green, and blue. All the colors of light are formed by different combinations of these primary colors. If red light, green light, and blue light are mixed together in equal amounts, they reflect all colors and produce white, as shown in the center of the model on the screen. Television screens and computer monitors take advantage of this color model. Tiny groups of red, green, and blue light shining at different brightnesses can produce all the colors on your screen. Each primary color has an opposite or a complementary color. The complementary color of red is cyan, and the complementary color of green is magenta. Then if you look at it, it says, what is the complementary color of blue? So hopefully when you are looking at what is the complementary color of blue, what do you see? The complementary color of blue would be yellow. Most objects in the world are not sources of light. Instead, they reflect light. The colors you see are those that are not absorbed by pigments in the objects. Pigments are opaque substances used to color other materials. The primary colors of pigments are yellow, cyan, and magenta. A lemon is yellow because its pigments absorb all colors except yellow. Yellow is reflected. Notice that the primary colors of pigment are the complementary colors of light. Now, this can be a little complicated to understand. Like I said, it's like the beginning of physics. But for now, just understand that these colors make up light. Now, when we talk about the primary colors of pigments, what I usually do in class is show you a printer cartridge. And this, of course, creates pigments or colors on your paper when you print something. And you will see on this cartridge the primary colors of pigment. They are right here. Hopefully you're seeing this. They're right here on those 3 dots. Cyan, yellow, and magenta. Those are the 3 primary colors of pigment that can be mixed to make all the different colors that your printer can print. Okay, so pigments. In nature, pigments are organic compounds that are part of the living thing. and it gives color to the plant or animal. Example, God gave a lemon yellow pigment. He gave leaves green pigment. In objects we see and use every day that aren't alive, pigments are the substance that is used to give color to other materials. Okay, so things that are not alive, things that we just look at, like your bike might be blue, your shirt is green, your jeans are black, whatever. All of those colors are created by pigments. Okay, so I'm going to show you a video that just explains a little bit about how are these pigments made that color everything that we use.
People have always used color as a means of expression. Prehistoric man created paint from a mix of dirt and animal fat or spit. Over the centuries, pigment production has become a lot more sophisticated. Chemical manufacturing produces synthetic mineral pigments to add color to the products in our world. From pavers to paint to plastic and cosmetics, this is where the color comes from, synthetic mineral pigments. They start with a salt recycled from the steel industry. In this case, it's iron sulfate, which has a bluish-green hue. They add warm water and they're ready for the next ingredient. High-quality scrap. It's another source of iron and it's about to be recycled into pigment. Crane claws transfer it to the mix. Chemicals are added. Every so often, a technician scrutinizes a sample of the yellow slurry. If he decides the color or thickness aren't quite right, adjustments will be made. The slurry now flows over a perforated metal drum with a filter cloth stretched across it as a spray of water rinses off the salt. The fluid in the yellow slurry is sucked through the filter cloth and into the drum, leaving a more concentrated pigment on the surface, called filter cake. The filter cake falls in chunks onto a screw conveyor and ends up at the top of a towering spray dryer. Inside, machinery presses the highly concentrated pigment through the holes of a rotating disc. This causes a spray of droplets that, when exposed to hot air, dries into pigment particles. This yellow pigment is now ready to be mixed into an emulsion paint for coloring wallpaper. A generous amount can produce a bolder shade. A little less, and it's a more mellow yellow. To make black pigment, they start with cast iron filings, another form of automotive scrap. This magnetic crane transfers the filings for production. And again, it will take a chemical reaction to produce the pigment slurry. The chemical reaction also generates energy that's recovered and used in the manufacturing process. They wash and thicken the black slurry on a revolving drum, just like they did for the yellow pigment. But this thick paste won't just be used to make black pigment, it will also be used to make red. For the dramatic conversion to red, the paste flows directly into a kiln, where it's baked until dry. They introduce air and increase the temperature to 850 degrees Celsius, making the black particle turn red. They transfer the red pigment to a drum, where they mix the pigment and adjust the color properties. Then they grind it to a finer consistency. Once the pigment is packaged in paper bags, it's ready for transport or warehousing. Like sugar, pigment comes in both a powdered and granulated form. This demonstration shows the difference between the two. The powdered pigment is more clumpy and doesn't flow from the opened end of the beaker. By contrast, the granular pigments are tiny microbeads that flow freely, which makes it desirable for users who want to mix and meter pigments more easily. To test how the pigment would color brick, they mix red pigment with a concrete substitute and compare the result to the standard to confirm that they match up. But sometimes, they need a real concrete example of a pigment's color tone. so they add a small amount to a mixer full of aggregate, water, and cement. The mixer rotates, and once the ingredients are thoroughly blended, they open the lid to reveal the red brick paste. They scoop it up for transfer to a brick-forming machine, and then fill brick forms with the paste. They activate a plunger that tamps it down to compact it into the forms, producing bricks. Red, black, or yellow, these pigments are sure to make things more colorful.
Okay, so that video just shows you, it doesn't show you how all pigments are made, but it gives you an idea about how pigments are made that color all of the objects that we use every day. We are now at the top of page 245. Paint pigments work the same way. You may have learned in art that the traditional primary colors are red, yellow, and blue. Pigments reflect these colors. Red paint looks red because it reflects the red. A blue crayon reflects the color blue. When you mix pigments together, you do not get white. You get a dark, almost black color. This is because they absorb nearly all of the colors of light shining on them. Color is a wonderful gift from God. When he said in Genesis, "Let there be light," he had already planned for his earth to be beautiful with color. He created the pigments and lights to work together. He knew that a wide variety of colors would bring pleasure to people. Now, just like I showed you my printer cartridge, when you look at Try It Yourself at the bottom, here's what it says. Many books and papers are printed by a 4-color printing process. The printers use combinations of cyan, yellow, magenta, and black ink to produce all the colors you see in a book. So if you've ever, I don't know if you guys change your own printer cartridges in the printer, but if it's a color printer, you've got this cartridge, which is cyan, yellow, magenta, and then I think I have a black cartridge here. Yeah, I do. Okay, and then the other cartridge is the black cartridge. So these 4 colors all combine together. Okay, and get back to my book. Use a magnifying glass to look at a colored picture in this textbook. Do you see all the individual dots of color? The dots are so close together that your eyes blend them together. This makes the color and shading that you see in the picture. So many things about light and color are fascinating. I have one more video for you that explains how does our eye see color anyway? How does it work? Here we go.
There are many ways that we use color. Artists use different colors to express emotions. Marketers attach colors to their brands to make them more recognizable. Animals use colors to ward off predators or attract mates, and people do too. What is color? Scientists define color as the limited range of light that we humans can see. We classify different types of light based on their wavelength, which can be anywhere from many meters in between each wave peak to lengths as short as the diameter of an atom. The full electromagnetic spectrum ranges from high-energy light waves with short wavelengths, like cosmic and gamma rays, to low-energy light waves with long wavelengths, like radio waves. The light we are able to see, called the visible light spectrum, ranges from violet light, which has a wavelength of about 400 nanometers, to red light, which has a longer wavelength of about 650 to 700 nanometers. But how do we perceive the visible light spectrum? When light bounces off an object, like this painting, into our eyes, it first hits the cornea, a film that lays on top of our eyes. This layer bends light towards the pupil, which dilates or contracts to let in more or less light. Once light passes through the pupil, it is sent to the lens, which angles and focuses the light to a point on the outer layer of the retina. Here, light-sensitive cells, called rods and cones, send information to ganglion nerve cells in the inner retina. Ganglion cells then send the information to the optic nerve, which sends the signal to the brain, where the signal is processed and interpreted. Rods and cones, the 2 types of light-sensitive cells located on the outer retina, have different jobs. Rods are responsible for our perception of light and dark and our peripheral vision. Cones are what allow us to see color. They are found in the center of the retina where light is focused. Cones come in 3 varieties, each sensitive to a different range of light. Interestingly, we have more cones sensitive to red light, meaning our vision is best for warmer colors like reds, oranges, and yellows. However, our cones aren't sensitive to light with wavelengths shorter than 400 nanometers or longer than around 700 nanometers. For example, a gamma wave's wavelength is about the size of an atomic nucleus, which is much too short for any of our 3 types of cones to sense. Radio waves are too long, with wavelengths longer than 2 Empire State Buildings put together. That doesn't mean that these forms of light aren't visible, per se. Other animals have different kinds and numbers of cones, which allows them to see the world differently than we do. Dogs, for example, are more limited in the wavelengths they can see because they only have 2 types of cones, leaving them colorblind to differences between red and green. Butterflies have 4 types of cones in their eyes, letting them see ultraviolet light. The animal with the best color vision might be the mantis shrimp, which has 12 different kinds of cones. If Pablo Picasso and Paul Klee created amazing works of art with just 3 types of cones, imagine the masterpieces the mantis shrimp would create with 12.
Okay, so that video shows you how your eyes see color with rods and cones on the back of your retina. Okay, that's all for this video of a crash course about light. Remember, what I asked you to do was write down 5 things that you either learned or found interesting. 5 things from this video, okay? And then when you get to the LMS quiz, there'll be 5 questions and each one will be like, tell me one thing you learned from the video. All I'm looking for is that you actually watch the video and that the 5 things you type in are things that the video talked about. Very easy to get an A+ on this assignment. All right, that is all for today, learning about light, and I'll see you for one more video about light before science is over for the year. See you later.